Well, thank you, Scott, for that excellent technology demonstration. And welcome everybody to this next session of the Microsoft Research Summit 2021. My name is Darren Edge. I'm a director in the Societal Resilience Group at Microsoft. And today I'm talking about using technology to combat human trafficking. Now, human trafficking and exploitation has no place in modern society, but it continues to flourish all over the world. In many ways, it's been exacerbated by the COVID-19 pandemic. And this is why fighting human trafficking forms a key part of our societal resilience research agenda, because only by elevating the condition of the most vulnerable people in society can we elevate the resilience of society as a whole. And when people think about using technology to solve a problem, they typically think about direct intervention. We have a problem, how can we build and use technology to take action against that problem? And Microsoft has built several technologies for direct intervention against human trafficking, including the widely used photo DNA service for detecting and removing images of child sexual exploitation. But today I'm talking about a different kind of technology that supports evidence-based policy. And the idea here is that given a problem, we make observations that create data. With that data, we do analysis that creates evidence, and with the evidence, we design policies that allow us to allocate many more resources, many people and technology to take action against the problem. It's policy, not technology, that allows us to have the greatest impact on society, but technology plays a critical role in helping this to happen. And so for the first example, technology can support feedback from action to design, helping policy designers to understand both the possible actions and the available technologies for making progress against the problem. So this was the challenge that arose through Microsoft's participation in Tech Against Trafficking, or TAT. This is a coalition of technology organizations working together to combat trafficking with technology. And the problem that we were facing was how to make sense of 300 or more anti-trafficking tools that have been surveyed by TAP members and painstakingly entered into an Excel spreadsheet. And our solution was to build an interactive map using features for exploratory data analysis that we'd already developed for Microsoft Power BI. And so here's that map in practice. It's accessible via the interactive map link on the TAT webpage. But let's dive in now and have a look at this tool list. So on the right, what you'll see is cards with an orange bar along the top representing the different tools and technologies that we surveyed. And the user can select any of these cards to look at the description and metadata associated with the tool to learn more. For example, they could click to navigate to the website. Now, if we look at all these cards in the tool, you can see that there's many more than somebody might reasonably be able to read through and understand in one sitting. And most people have a particular question in mind. So if your interest is in tools, for example, about data trends and mapping, you can select that using a summary visual on the left to filter down that collection of tools that you're viewing and exploring on the right. And 15 is a much easier number to read through than 309. If you're also interested in data trends and mapping in the public sector, you could continue drilling down into the tool to see a progressively smaller set of tools for analysis and research. And here we can see the Counter Trafficking Data Collaborative. This is one of our major partners, and you'll learn much more about CTDC later in the talk. So all of these tools, are summarized in various ways, including these categories that we have applied as experts in the space, as well as key phrases extracted using NLP. If you have a particular query in mind, though, say you heard somebody say CTDC is doing great work in the counter-trafficking space, you could always just search for any of those keywords, and it should take you directly to the tool. Okay, so let's go home now and start looking at different ways in which we can map out this space of tools. And in particular, let's look at tools in terms of how they relate to different categories and sectors. So in this network visualization or network map on the right, we can see all of those tools shown again as orange circles, and they're connected to these blue nodes, where the blue nodes represent different kinds of tool category and different kinds of sector that you may be interested in. So for example, this large blue node represents cross-sector tools. You can see that's quite an important attribute in the space. And this other blue node we're going to zoom into now represents tool category of victim and trafficker identification. So all of these orange tools connected to both of them are tools that are both cross-sector and for victim or trafficker identification. If we'd like to get a clearer view by zooming into the map, we can filter on something of interest, like victim or trafficker identification. That puts it in the center of the map, and then we can start beginning to explore these clusters of tools used in different sectors in this instance. So we can see there are many tools for cross-sector work, but fewer tools for other areas. So for example, if we're thinking about tools in the financial sector, there's just one here. And if this is the kind of tool we're looking for, we can click to learn more, and perhaps we found a tool that we can go and use to help combat the problem in the space where we're working. Okay, so the second way in which technology can support evidence-based policy is by helping policy designers to develop evidence from data and to do so themselves using their domain knowledge. So this is a motivation behind the tool that we've developed called Show Why. Show Why enables domain experts to evaluate causal questions over real-world data via a guided process that assumes very little background knowledge in data, statistics, and causal inference. It emulates randomized controlled trials to the best extent possible using observational data that's already been collected. And this is based on guidelines developed by our partners at Johns Hopkins University and Stanford University that were developed in the context of looking for off-label kind of drug application in the fight against COVID-19. Show also evaluates many alternative specifications, both of the question and the analysis, to reveal the impact of decisions and assumptions that might not appear to be all too important. They could be essentially arbitrary, but might have a very outsized impact on the estimates that are produced. And finally, Show Why encourages interactive presentation of the evidence that's developed in the tool, as well as reproducible analysis by exporting reports and code in the form of Jupyter Notebooks for independent review and audit by people who are data scientists. And it's called Show Why because it's powered by causal inference using the Microsoft Research Library DoWhy, as well as EconML. Okay, so let's dive into the tool now and see how it works in a problem in the human trafficking space. So here's Show Why. We're going to load the project, and this is going to help us to answer the question, for identified victims of trafficking, does recent natural disaster cause the severity of control that the victims experience to increase? And there are various reasons and theories in the field as to why this might actually happen. So we can document kind of this general question. We can think about different ways of instantiating each of those elements of the question. So for instance, how are we going to define the population, the exposure, and the outcome? The tool asks the user to think about all the possibly relevant causal factors, as well as how they might be linked to the exposure or outcome, either by causing them or being caused by them. And then equipped with this information, Show Why can construct a causal graph of the causal relationships that operate in the domain. This is a representation of the user's domain knowledge. So here's a simplified example of that graph, only showing what's relevant to this particular problem. We can kind of click this button to ask do why on the back end to verify that it's actually possible to estimate the thing that we care about using this causal model. And we can look at different levels of model derived from causal relationships where we have different degrees of belief, all the way down to an unadjusted model where we're simply ignoring anything that might be a confounder and seeing what kinds of results we get. So in general, we get much more valid results by employing our domain knowledge. So we're skipping ahead several stages now, looking at some results. What we're seeing along the top of the screen is a selection of estimates of the effect size. So 0 is no effect, positive is a positive effect on the outcome, below 0 is a negative effect. And we can see that there's a wide range of results. Some of the ones I'm pointing to here came from the unadjusted model. Again, I said that's a bad idea. We really should try to capture our domain knowledge so we can eliminate those results. Next, we can start thinking about which of the other models that we use were the most valid. Well, the minimal model here appears to be applying some downward pressure on the effect sizes. And if we kind of bring in these visualizations here, we can see that the machine learning that we've done on the back end is actually suggesting that this is giving a downward pressure that we don't want. And actually, if you think about the way we constructed that model, it only accounted for age and gender. And so we actually want all of the data from all of the potential confounders. Our estimators don't appear to make much difference in terms of systematic pressure on the effect size up or down. What it does is how we define a severe disaster. So again, we can see that if we look at the top 50%, then it's pulling our estimates down. But actually, we're only really interested in the most severe forms of disaster. So it's okay to eliminate those specification elements. And so what we're left with is different ways of defining the population. We used two ways. One was looking at only those records where they had no missing data. The other one was looking at records where we had imputed missing values. And what we can see here is that it doesn't really matter which one we go with, so we might as well include estimates from both. Now we can start looking at individual estimates and seeing whether they passed what's called refutation. So the various tests we can do to see how valid those estimates might be based on challenging the assumptions behind them. And so what I'm doing here is I'm just systematically getting rid of any estimates where they didn't pass all the refutations that we tested them against. And at the end of this process, what we're left with is a handful of estimates that represent our best guess about the effect size for the question. So almost there. Yes, all of these passed. So, we're looking at the conclusion here that, for our question, exposure to recent natural disaster in the top 25% of disasters looks like it increases the severity of control or the chance that the victim will experience a severe means of control by around 30%, which is quite substantial. So this is not a peer-reviewed finding. This is just an illustration, but hopefully it shows you how somebody working in the domain could kind of go through a very rigorous process to understand the causal kind of factors that are operating. And at any point in the process, you can download a report that tells you everything step by step. Okay, so the next way in which technology can support evidence-based policy is by creating feedback from analysis to observation. How can we help policy designers to access and analyze private data on vulnerable populations that couldn't otherwise be shared because of privacy or data protection concerns? So this challenge also arose in the context of Tech Against Trafficking and the 2019 Accelerator Program with the Counter Trafficking Data Collaborative, or CTDC. So CTDC is run by IOM, the UN Migration Agency, and it pools data from IOM, Polaris, and Liberty Shared, and others to create the world's largest database on identified victims of trafficking. And a subset of this data is made available through the CTDC website after it's been de-identified and anonymized using a technique called K-anonymity. And the problem that CTDC were experiencing is that this suppressed 40% of the cases in their database. And of the remaining cases, if you look at the attribute combinations that were left, 40% of those were unique. And it's potentially linkable to unique individuals in the world. If we look at combinations that describe small groups of individuals below 10, that was 80% of the combinations. So this was a real problem. So our solution is to generate synthetic data only from attribute combinations that are common in the sensitive data. This means that if we give you a synthetic data set and you identify a combination of attributes that looks like it describes a unique individual, we know by construction that actually it describes a much larger group and so can't be linked to any of those individuals. Now, if I give you some synthetic data that meets these guarantees, that's great, but you might not believe it when it comes to estimating a count of victims in some particular group that you care about. And that's why, along with synthetic data, this pipeline also generates aggregate data pre-computed from all short combinations of attributes. And we also generate data dashboards in Power BI that allow users to interactively explore and compare these data sets. So this tool was used by our partners at IOM to create the first CTDC Global Human Trafficking Synthetic Dataset, which was released in September this year. And you can access the dashboard that allows users to interactively explore this by scrolling to the bottom of the page. So let's have a look at this dataset now. So on the left, you're seeing lots of estimated counts of cases derived from the synthetic data. And on the right, you can see how those synthetic estimates compare to the actual estimates that we pre-computed in advance. And what you'll notice is that, at least initially, before you start drilling down, those counts match precisely. So this is one of the ways in which we guarantee the utility of the synthetic data set. If you're interested in the count of any one thing by itself, that count is precise, modulo a privacy resolution that prevents the disclosure of precise counts. So you can also see that there are very many combinations, very many attributes rather, in this data set. Let's start drilling down into some of them now. So let's look at cases where the year of registration was 2019. We make that selection and all the other counts filter to show us the counts of cases only within that year. And we can see that our estimates from the synthetic data very closely track the actual values after drilling down on that year. So next, let's look at female victims of sexual exploitation in the USA. Again, we can see that after selecting these three attributes, again, the estimated values track the actual values quite closely. Now, if you notice these results here, we're seeing an example where we have an estimated count of 1. So that's a combination that's unique in the sensitive data set. But actually, this describes a group of 30 individuals in the sensitive data set. And so it's not a privacy risk in the way that it might otherwise be. So as we keep making selections, at some point we reach the limit of the combinations we pre-computed. And at that point, you have to just rely on the aggregates that you get from the synthetic data. And as you've just seen, this is very good at capturing the dominant patterns in the data. But let's also now look at a smaller group. So here I've noticed that Federated States of Micronesia citizens are being exploited in the USA. And we can see that this is a small group of around 100 individuals. And the synthesis process has captured that group kind of really accurately. Let's now look at, again, some other aspects of the data. We have data on types of exploitation in terms of labor and sexual exploitation. And we see some evidence of crossover here in terms of the hospitality sector and prostitution. And we can also notice that this appears to be a particular problem for citizens of Cuba being exploited in the United States. So again, this is not conclusive evidence that this is a big problem, but it's evidence of a problem that might warrant further investigation. So finally, let's look at some recruiter relationships. So if we look at victims recruited by their intimate partner, we can see that this is predominantly associated with sexual exploitation of females. The same is true for family recruiters. But once we look at friend recruiters, we see that forced labor is the top type of trafficking. And if we look at forced labor specifically, we can see that males in this instance actually outweigh females. So finally, let's have a look at victims who've been trafficked for a very long time, 5 or more years. And again, taking a global view, we can see that this appears to be, quite a problem for citizens of Myanmar who have been exploited in Indonesia. Okay, so again, this is not conclusive evidence of anything in particular, but it's an exploratory form of analysis that generates hypotheses you may wish to then go and evaluate using other tools, which we'll get to next. So another way in which we can use technology to support evidence-based policy is by creating feedback from observations to actions, helping frontline workers to identify emerging patterns and trends that might have important policy implications. Again, this arose in the context of the ongoing Tech Against Trafficking Accelerator with Unseen UK and Seattle Against Slavery. Now, in both cases here, there's a need to detect meaningful changes in real-world data streams. And for Unseen, this was cases reported to the UK's Modern Slavery and Exploitation Helpline. And for Seattle Against Slavery, this is in online ads for commercial sex, where changes in terms of the attribute contents of those ads might indicate scam ads that, if they're used by Seattle Against Slavery, can create unnecessary volumes of spam for their outreach workers. And so it's something to work to avoid. So let's have a look at how our technique works. So we model the problem as a dynamic graph of attribute combinations. And we use a technique developed by our collaborators at Bristol University called Unfolded Adjacency Spectral Embedding, or UASE, to look for meaningful changes in this graph structure. This is something that we're working towards building into our Graspologic toolkit for graph statistics, making available on GitHub later this year. So let's now kind of have a look at how this works. And we're using the synthetic data set from CTDC to create this shareable example. So here we are. This is a standard way of looking at data in a tool like Power BI. We're summarizing it in terms of various attributes. Now we're looking at victims registered in 2019. So we can see the subjects who are registered in that year. We can select one. We can see all the attributes associated with those subjects. So this is interesting, but we're moving between two extremes, the population level view and the individual. We think there's value in the patterns of attributes in the intermediate scales. So here we're creating a graph that connects attributes of case records based on the number of victims that have both of those attributes. So we can see that this structure changes over time, but it's very hard to understand what is changing and what is staying the same. So with the embedding method that we're using, we can actually measure how much attributes are changing their behavior compared to their average behavior over all other periods. So this is where we can start looking for the emergence of patterns. We can also use the embedded space to say, okay, so a node is moving. What is moving towards it? For any selection that we can make in terms of the nodes, we can see that some nodes, other nodes in the embedded space are moving towards it. They're becoming more related. Their behavior is becoming more similar in this time period, and others are moving away. And in general, in any time period, there are lots of things kind of moving in lots of different directions. But by looking for groups of attributes that are all converging on a given point, they're all getting closer to one another, we can start to identify the foundations of really meaningful patterns that emerge despite a very noisy data collection process. And so on the next screen, you can see how these turn out. So we're looking across the entire data set now, saying what are the most salient patterns based on our definition of salience. So you can see that the top rated pattern here is female citizens of Indonesia exploited in Malaysia in 2006. We're defining salience based on a combination of factors, including this notion of convergence, which is our measurement of how strong these attributes are converging within this space. We can compare that salience and when we see spikes in that salience to other indicators of what's happening in the real world at the same time. And so we can kind of maybe argue as to why this spike in the cases we're seeing could be related to some underlying change in the real world trafficking process. So in the second example, we're looking at victims aged 39 to 47 in the Ukraine in 2020, and the spike that we're seeing does coincide with number of people affected by disaster in that country in that year. So we can see this again for female citizens of Haiti, obviously affected by the 2010 earthquake. And if we look at the time period where we detected the most interesting kind of patterns, we can see that in 2019, the top pattern describes that group of citizens of Micronesia exploited in the USA. So this happened in 2019. And again, if we look at the impact of disaster on Micronesia in that year, we can see that around 30% of the population were impacted. And this was actually a typhoon that hit Micronesia at the time. So again, some plausible connection between something happening in the real world and some insight we've been able to derive from the data set. We have several more insights from this data. So here we're seeing male citizens of Mexico exploited in the US agriculture sector. And again, this is a pattern detected out of a million or so potential patterns of that length, but our tool has picked it out as being particularly meaningful given all behavior of all attributes over all time. And this also applies to Cuban citizens exploited in the hospitality sector and involved in prostitution in the US in 2019. Again, this might be linked back to some disaster that appears to have peaked in 2017. Okay, so I've been talking about using technology to combat human trafficking, in particular by building open tools to support evidence-based policy and collective action at the speed and scale needed to help combat the trafficking crisis. And I presented 4 tools today, but ultimately this is not about the technology. It's about building technologies with trusted partners in the community and making those tools and results available to the community at large. So I'm very pleased to announce today that Microsoft has now joined the Telfinder Alliance, and we're looking forward to working with Telfinder Alliance on furthering the cause of evidence-based policy in the fight against trafficking. And ultimately, it's policy that allows us to elevate the condition of vulnerable individuals around the world and build a more resilient society for everybody. And so for more details about all our efforts to help build societal resilience, please navigate to aka.ms/societal resilience and select research. Thank you very much.